When we classify matter, remember that all matter falls into two basic categories: homogeneous matter or heterogeneous matter. Now, by definition, heterogeneous matter is going to be a mixture. Now, mixtures are simply combinations of pure substances. When we talk about mixtures, though, mixtures can be further separated into heterogeneous mixtures or homogeneous mixtures. And again, look at how we compare these. Heterogeneous is not uniform, okay, whereas homogeneous is uniform. Heterogeneous, the components are disproportionate. I have an unequal amount of parts. And in addition, heterogeneous mixtures can be seen by the naked eye. The next thing I want you to notice is the difference in the particle diagrams here. You really want to be able to distinguish and draw and diagram the particle diagrams for mixtures and pure substances. Now, whenever we have a mixture, the main thing to remember is that all mixtures retain their identity and they retain their properties. And that retention of properties is what allows any mixture to be separated. So I can separate a mixture strictly because it retains those properties. So when you look at the combination here of iron and sulfur, if I mix that up, I can still apply a magnet and separate that iron from the sulfur because it retained that property. So the different techniques that we can take advantage of for separating mixture really fall down to the type of mixture we're dealing with. If we have mixtures of liquids, we take advantage of distillation because this is differences in boiling points. So because they'll boil at a different temperature, I can literally distill them. This is how most of our petrol, anything that's crude oil based, so kerosene, diesel, gasoline, all of those things that we use, we separate through their different boiling points. In essence, if you boil away a liquid and leave a solid, it's sort of a distillation because there's definitely a difference in the boiling point. Filtration is another method, and filtration takes advantage of the different, whether I have something solid and liquid, takes advantage of the different sizes of particles that are put together in the mixture. And then we also have chromatography, and this has to do with the difference in the solubility of a solvent. So here we have a solvent that's going up our paper, and the attraction of the ink here to both the solvent and the paper is what allows this to be pulled apart. But ultimately it is a physical property because solubility is simply a change in appearance. It doesn't change the property or the identity of the substance. And we know this, for example, when you put salt in water, the water tastes salty, and that's because of that retention of property. Now, pure substances, on the other hand, are different in that we see the fixed composition. Okay, our particle diagram for the mixture shows obviously different things present. Whether they're present equally or unequally, it's still obviously completely different substances there. When we deal with a pure substance, it's all one thing. Whether this thing happens to have atoms combined in a compound or whether it's elements, it's still a fixed composition. Notice also that the properties are identical no matter where no matter what. So if I get down to the smallest particle, in the case of compounds, if I get down to, look at water. So let me draw water here real quick. If I have water, I have an oxygen atom and two hydrogen atoms, okay? At the smallest level, that molecule has all of the properties of water itself. So we have a very specific characteristic set of properties that identify and distinguish water from other substances, and this is true for identification of density, boiling point, melting points, how it behaves with other substances. And it's always the same composition. In other words, again, it goes back to this idea of a fixed composition. So it's exactly the same ratio of individual atoms comprising it. Now, when we deal with compounds, by definition, they are combinations of atoms. They are bonded together. Whether that bond is covalent or ionic, which we'll discuss later, it's still bonded together. And it's defined by what's known as the law of definite proportions, meaning salt, sodium chloride, is always 1 sodium to 1 chloride. Water is always 2 hydrogens to 1 oxygen, no matter what. Elements, again, remember from previous science classes, elements, we see them on the periodic table. They have defined properties, they have defined characteristics. We organize them in families or columns and periods, and ultimately we have 3 types of elements: metals, metalloids, and nonmetals. Now, one of the things I want to point out here that they're showing you in the diagram is they're basically showing you what we know as diatomic elements. So notice, remember that diatomic means 2 atom, so diatomic, and di meaning 2, and it's 2 of the same atom bonded together, and they're still elements. We'll also see element diagrams where you just have the individual atoms.